In this video, I'm going to do some review notes for your test. First and foremost, the most important thing you should be able to do, you should be able to identify and justify which method to use for factoring quadratic expressions and solving quadratic equations. So you should be able to identify and justify which method to use to factor quadratic expressions and to solve quadratic equations. All right, so factoring you do when you see an expression, and solving you do when you see an equation. So if you see an expression on the test, you're going to factor it. If you see an equation on the test, you're going to solve it. It says what to do in the question, but just in case, just make sure that you're doing that right. All right, so to start, we're going to talk about the methods for factoring expressions. So the methods for factoring expressions. And I'm going to put that in pink or purple or whatever color that is. All right, so the first method that we talked about was the diamond to factored form method. So the diamond to factored form. And that method we use when we want to factor something that's ax squared plus bx plus c form. We have a is equal to 1, and I can find two numbers that multiply to c and add to b for that ax squared plus bx plus c form. So so they have to add to b and multiply to c. All right. So that was the diamond to factored form. It's when a is equal to 1 and you have the form ax squared plus bx plus c. So the form ax squared plus bx plus c. Sorry, I lost my train of thought. And just a is equal to 1 is really important there. All right, the second one we talked about was diamond to expanded form. So diamond to expanded form. And that's when we have the form ax squared plus bx plus c form. But a is not equal to 1. And still, I can find two numbers that multiply to a times c and add to b. So they multiply in this case when a is not equal to 1 to a times c, and they add up to b. And the important thing to note here is that this is when the coefficient for x squared is not equal to 1. Then the third method that we talked about factoring was the difference of two squares. And the difference of two squares, or I didn't underline the other ones. The difference of two squares, we have only two terms. So we have ax squared and c no b, no bx. So there's no bx. And there's subtraction in between those two terms. That's important because it's the difference. So it's not when we have addition. There's subtraction in between. And both terms are perfect squares. Okay, really important, both terms are perfect squares. Okay, they have to be perfect squares to be the difference of two perfect squares. All right, and then, sorry, this was the one I was supposed to talk about first. Its greatest, and I'll put it in capital letters, common factor. And this always check first. So always check first. And I'll leave enough space to write that. Okay. Greatest common factor. And this I know I can use when all terms, and you want to use it first because you'll have to do it at the end if you don't do it first, and it will be harder to remember to do that. So do it first when all terms have something in common. So you look for that first. And that's the first method of factoring. And then from there, after simplifying, you look to see what you can do based on the other three things, like what form you have. All right, so that's factoring. Next, let's talk about, let's talk about examples with that. So I'm going to make a table here. I wanted that to be longer. Here. I can't. Okay, there we go. All right, so I'm going to make a table here. I'm going to put... Okay, so I'm going to put some expressions. So I have 6x squared plus 11x plus 3. And I want to know which one of these things am I going to use. So I'm going to check the diamond because this is ax squared plus bx plus c form. So I'm going to check if it works. I have 3 times 6, which is 18. And I need the numbers to multiply to that and add up to 11. And I can find two numbers, 9 and 2. So since the diamond works, I know that this is going to be the diamond to expanded form since I have a 6 in front of the x squared. So it's diamond to expanded form is the method that I'm going to use. If I had x squared minus 9, I can see very clearly this is the difference of two squares. And I'm not writing the reasoning why because I just talked about the reasons why I know that. But the reason why is because I have two terms that are perfect squares, subtraction in between. What if we look at 2x squared plus 24? Well, that's two terms. And it kind of looks like if I took the 2 out, it might be two perfect squares. But it's not actually, because if I took the 2 out, I have, this is going to be 2 times x squared plus 12, and that's not perfect squares, and there's not subtraction in between. So I know the only thing I can do here is GCF, take out that 2. If I have something like 8x squared minus 18, the first thing I would do is I would factor out my greatest common factors. So I know that would be one of my methods that I would use. So I factor out 2, and I have 2 times 4x squared minus 9. Now this is going to be inside here, the difference of two squares. I have 2x to the second power here, 3 to the second power here. That's two perfect squares, subtraction in between. So I start with GCF, and I also have the difference of two squares. And then for 4x squared plus 6x plus 2, I have, first things first, I can take out a 2 for all of these terms. They all have a 2 in common. So I really have 2 times 2x squared plus 3x plus 1. And then I look to see, is there something I can multiply, or there are 2 numbers that I can multiply to get 2 and have them add up to 3. And yes, that's 2 and 1. So since the diamond works, this is first GCF because I have to pull out that 2 first. They all have something in common. And then after that, I would do diamond to expanded form. So this would be two examples, right? 2 different methods here as well. Just one method here, one method here, one method here. I don't know why I had to go through all that. Then I have x squared plus 6x plus 5. This is ax squared plus bx plus c form, where a is equal to 1. If I can use the diamond to find 2 numbers that multiply to 5 and add to 6, that's 5 and 1. Yes, I can. That means that I can do diamond to factored form. If I have x squared plus x minus 3, I'm looking to see if the diamond works. I need 2 numbers that multiply. Let me do this a little bit over here. I need 2 numbers that multiply to -3 and add up to 1. So -3 and 1, no. 1 and 3 and -1, and no, that doesn't work either. So there are no 2 numbers, which means this is not factorable. So I would write not factorable. Can't factor that thing. I could solve an equation if it was equal to 0. I could use the completing the square method to do that, but I can't factor it. Then if I have x cubed plus x squared minus 3x, I know all 3 of these terms have something in common. They have an x in common, so I could take out an x. I have x times x squared plus x minus 3. I already checked that from here, and I saw that it was not factorable, so the only thing here is GCF, and that GCF is that x that I pulled out. And then, let's see, 4x squared minus 25. That's the difference of 2 squares, 2 perfect squares, subtraction in between, and it's 2 terms, which I just said. So a difference of 2 squares. Okay. All right, so that's just examples listing what you need to do on your test. You're going to need to explain why you know that that's the method. So the reasons why that's the method are all up here. But I want you to put it into your own words, not just copy what I wrote. Okay. All right, so I have methods of solving. So methods of solving. And now we're talking about quadratic equations instead of expressions. So the first one that we check always is factoring. We want to check factoring first. The different examples of factoring. If we choose factoring, we need to also specify what are we actually using. GCF, you check that first. Diamond to expanded form, diamond to factored form. We have diamond to expanded form. We just talked about all of these and the difference of 2 squares. So, of 2 squares. So I know for factoring, if I have any of these things will work after I simplify to have 0 on one side and everything else on the other side, then I know I'm going to be using the factoring method. So I know that GCF exists if all terms have something in common. I know that diamond to factored form works, or both of these two work, if I have ax squared plus bx plus c form and the diamond works. So that's how I know it's factorable. And then for this one here, the difference of 2 squares, I know that works if I have 2 terms, both perfect squares. and subtraction in between, which we just talked about. Okay. All right. Next thing is the square root method. So you can use the square root method if it's not factorable. Even if it is factorable, you can use the square root method if you can simplify to two terms. So if you can simplify to two terms, and those two terms, those two terms are something squared. So those two terms need to be something squared and a constant. So something squared and a constant, if you have two terms, you know you're using the square root method. That's the easier one to use than the difference of two squares. So if you can, use the square root method instead. The other one is completing the square method. So completing the square method, and that one you use, the pattern is, if you have, it's not factorable. So first off, it's not factorable. And you can simplify so the first thing you want to do is you want to simplify the expression, the equation, to have everything on one side and 0 on the other side. Or, you really just want to simplify it to get it into a form that you know. So can simplify to 3 terms in ax squared plus bx plus c form. So this is the first way that you know if you have completing the square method. Then you check the diamond if the diamond doesn't work. So if diamond doesn't work, it means it's not factorable, which we already said. Doesn't work. I can't find the two numbers that multiply to whatever I need and add up to whatever I need. And these 3 terms, so those 3 terms are going to be ax squared, bx, and c. And the thing that makes it different from the square root method is that I have that bx. So the bx is what changes it. Oops. Is different from the square root method. And then the last one we talked about, the last one we talked about is the quadratic formula. So the quadratic formula can be used in any cases. You're only allowed to use it once on your test. You need the form ax squared plus bx plus c is equal to 0. If you have that form, you can find the roots by doing x is equal to negative b, plus or minus the square root of b squared minus 4 times a times c all over 2 times a. And then to go over some examples. So to go over some examples, I'm going to make a little table of where we would choose which method to use. I meant to make that bigger again. Oh my goodness. These things are so frustrating. Okay, here we go. So I have let's do the column. I'm really bad at straight lines. Really bad at straight lines. Whatever. Okay, so this will be the simplified version because I want the first thing I'm going to do is simplify it. If I start off with 5x squared minus 20 is equal to 0. The first thing I really want to do there is I want to divide everything by 5 because I know that all these terms have 5 in common. So if I divide by 5, that's not technically the GCF. You could take out a 5. You could rewrite this as 5 times x squared minus 4 is equal to 0. You could do that. But it's easier for equations. You don't even have to bother with the GCF. You can just get rid of it. by dividing. So I'm going to do that instead. So I divide both sides by 5, and I'm going to end up with x squared minus 4 is equal to 0, which I know I can factor because that's the difference of two squares. So I could say I use GCF there if I want to. It doesn't hurt. And I could say then I'm going to have to use the difference of two squares. So I'll have to use the difference of two squares. For an example that looks like this, so I have x squared minus 30 is equal to 0. I know if I simplify that thing, I can't simplify that thing. That thing is already as simplified as it will be. I have two terms there, but they're not perfect squares. So, but I do have something squared and a constant. So I know I'm going to use the square root method. And what will make that super clear is if I add 30 on both sides here, add 30, I'm going to get, this is x squared is equal to 30. And then I can see I could use the square root, take the square root of both sides to find my answer. All right, so another example would be x squared plus 50 is equal to 0. Again, I don't have subtraction in between. These are not both perfect squares, but they are two terms, something squared and a constant. So I could rewrite this as x squared is equal to negative 50, which could very easily show me that I could take the square root of both sides to find my answer. So this is, again, is the square root method. Oh my gosh. Square root method. And then for another example, if I have 5x squared minus 20x plus 3 is equal to 0. If I simplify that thing, there's no GCF I could take out. It's already an ax squared plus bx plus c form. So I know that, but I do want to check to see if the diamond works. So I do 3 times 5, which is 15. I need two numbers that add up to, multiply to 15 and add to negative 20. And there are no two numbers that do that. So because the diamond does not work, I know this is not factorable. I think completing the square would be a nightmare because of that 5 in front of the x squared. You need to have to divide everything by. So the best method to use here would be the quadratic formula, because you can use that for anything. The other methods are all hard to use for or impossible to use for this. And then if we do x squared plus 4x plus 3 is equal to 0, I know that this is, the left-hand side is factorable, since if I check the diamond, this is not the simplified form, just so you know. If I check the diamond, I'm finding two numbers that multiply to 3 and add up to 4, which is 3 and 1. I can find those numbers. So since the diamond works, I know that this is factorable. So I could use the factoring method, and it's diamond to factored form, since a is equal to 1. All right, up here I messed up. I called this GCF and difference of two squares, but I was supposed to say it's the factoring method. And then I was supposed to say in parentheses, it's a GCF and then the difference of two squares. Or you could just say difference of two squares for that. All right. Let me think if there's another type of example we should go over. Square method. Oh, completing the square. Okay. I just told you the answer, but if we have something that looks like x squared plus 6x minus 3 is equal to 0. This would be an example of where completing the square would be good. If I check the diamond, I need two numbers that multiply to negative 3 and add up to 6. And I can't find two numbers that do that. So this would be a good example of where I would use completing the square. Because the diamond didn't work, so it's not factorable. But it would be easy for me to use completing the square as opposed to a quadratic formula. All right. And then the other thing that you need to know is complex numbers. So complex numbers, for that you need to know I is equal to the square root of negative 1, by definition, and that's because by definition, I squared is equal to -1. So this is the definition. Oops. This is by definition. We define I squared to be -1, and then taking the square root of both sides there, we see that I is equal to the square root of -1. That means I cubed is, if I do I squared times I get it's -I. And then I to the 4th power, I can break down into I squared times I squared, which I know is -1 times -1, which gives me +1. So these are the 4 things that you need to know. All right. The other things that you need to know, you need to be able to convert, you need to convert non-real numbers to imaginary numbers before performing operations. So you need to convert non-real numbers to imaginary numbers before performing operations. Okay. You always convert to real numbers when you can. So you always convert to real numbers when you can, which means if you see I squared, always change it to -1. And no imaginary numbers in the denominator. That's important. No imaginary numbers in the denominator. So if I have something like 5 over 4i, I can multiply the top and bottom here by I. I want to get I. So I can multiply by a giant 1, I over I. I want to get I squared in the denominator so that turns into 1. So this will become 5i over 4i squared. I know I squared is -1, so this is just 5i over -4. And I've gotten I out of the denominator. If I had something like 5 over 3 plus 4i, I would need to multiply the top and the bottom by the conjugate of the bottom so that I could get a I squared term and a constant by itself in the bottom. And that's what happens when you multiply an expression times its conjugate. It's the difference of two squares, which in this case, since I is our variable, would be I squared minus some constant. So 3 plus 4i times, oops, I guess I should just, I'm multiplying by the conjugate, 3 minus 4i in the top and the bottom. This is a giant 1 that I multiply by, so I can get rid of the fake numbers in the bottom. In the top, I'm going to have 5 times 3, which is 15, and then 5 times -4i, which is -20i, all over in the bottom. I should just know at this point that if I multiply something times its conjugate, some expression times its conjugate, or two-term expression times its conjugate, I have the difference of two squares. So really I have 3 squared minus 4i squared. And that's going to give me 15 minus 20i all over, this is 9, and that's going to be, I have to distribute that 2 to both the 4 and to the I. So I get minus 16i squared. That's 15 minus 20. We already did an example like this. Over 9 plus 16, which is 25. And then I can take out, I can take out a 5 in the top and the bottom. And I'm going to end up with 5 in the top and the bottom. Times 3 minus 4i all over 5 times 5, and the final answer is 3 minus 4i over 5. Okay, and then, so no imaginary numbers in the denominator. And then another thing that's important is real numbers come first, imaginary numbers last. So put your real friends first to remember that. Okay. That's what you need to know about complex numbers. Review the review sheet. That will be helpful for you for your test. review these notes. And I will see you on Thursday or Friday.